All right. Now let's take a look at some more things with respect to the Pickett's existence uniqueness theorem, and then how this nicely works out in dealing with something called the phase plane and phase portrait and autonomous differential equations, and also we'll talk about stability of all these things, right? And also we'll talk about some applications, and that takes care of this chapter. So let's take a look. So before I go any further, I want to take a little bit, deviate from whatever we are doing. I want to take a step back, and I want to show you some geometrical, nature of the solutions and so on. So let's take a look at, take a step back and try to visualize how the solutions are geometrically. So let's take a look at this, the same similar problem, the same problem. Let's take a look at this one and try to visualize it, right? Try to visualize the solution to this. So we know we already solved this problem. Y prime is equal to y, and we have the initial condition, that is y of 0 equal to 0. As a matter of fact, we can solve this problem. We can solve this initial value problem. And this is, since it's y prime is equal to y, the one parameter family of solution is y of x is equal to a constant times e to the x. And since the initial condition is y of 0, which is equal to 0, which is equal to c times e to the 0, which is equal to c times 1, which is equal to c. So that tells you your c is equal to 0, right? So this tells you your c is equal to 0. And so therefore, if I put all these two together, the solution is y, as a matter of fact, is equal to c0 times e to the x. Well, it doesn't matter, it is still 0. So the solution that we get is y equals 0. So if I try to graph it, if I try to graph it, the graph looks like this. So the solution, here's the differential equation, and the solution is supposed to start here, right? X is 0, y is 0, as you have seen in here, right? As we have seen in here. As we have seen in here, the solution is supposed to start here, right? And we found, as a matter of fact, we found the solution. The solution is, as a matter of fact, the solution kind of, goes this way. It's this line right here. As a matter of fact, it's a straight line, it's x-axis. And the Pickett says there's only one solution, which means you will not have another solutions going like this. That's impossible. That's not possible, right? You're going to have only one solution, and that one solution is y is equal to 0. Now, if I ask you the question, what happens if the solution that starts at this particular point, where x is 0, but y is equal to 1? X is 0, y is equal to 1. Then we are looking at this particular initial value problem, which is y prime is equal to y, and y of 0 is equal to 1. That's an initial value problem. I'll let you solve it in the interest of time. If you simplify everything the same way we did, we are going to see that y of x is equal to 1 times e to the x. Your constant is going to be, the arbitrary constant is going to be 1. So it's going to be e to the x. That means we're going to have this solution right there. Again, this is an initial value problem, very nice problem. So therefore, as per the Pickett's, I will not have another solution that passes through this way. There is no way I can have it, right? I will not have another solution going. I may have another solution somewhere here, but it cannot intersect over here. If it passes through this particular point, right? There's only one solution, and that one solution is y is equal to e to the x. Let me reiterate one thing in here. For the same differential equation, when you have an initial condition here, I have one solution. When I change an initial condition here, I have another solution. These two are two different solutions coming off of two different initial conditions. But for the same initial condition, for the same differential equation, I'm going to have only one solution. That's what we call initial value problem, right? For an initial value problem, I'm going to have only one. And then if I take a look at another one somewhere here, if I take a look at, let me go with the orange. If you take a look at a point right here, and this point is x is 0, y is equal to 1, right? I will have a solution, go home and try that solution, which is going to be the differential equation is, the initial value problem is going to be y prime is equal to y, and y of 0 is equal to 2, right? Y of 0 is equal to 2. And the solution to this is, try it later, verify, is going to be 2e to the x. And that's going to look like this. That's going to look like that. And now the next question comes, right? We can think about the next question. Next question is, so I have a solution to the initial value problem. I have one of them here. I have another one here. I have another one here. Is it possible? Is it possible I have another solution that is starting somewhere here and intersect? Is it possible? Right? Is it possible? The answer is it depends, but in this particular one, I can say no. The reason it's a no is uh, in this particular problem, it's no is this we can prove, we can state since this function right here is continuous in the entire real line. And since the partial derivative is continuous in the entire real line, this initial value problem satisfies Pickett's theorem in the entire real line, therefore the entire real plane. So therefore, for this particular problem, because it satisfies on the entire real line, for this one, you're going to have a unique solution on the entire, real line. If you have a solution there, the solution will never intersect with anything else because of this, the nature of the functions that we have, right? There may be another problem where the function might not be differentiable at some point. Then I don't know, right? Or the function might be differentiable only in the interval of, let's just say I'm just making this up, right? 2 to 5. Then I can guarantee the solution in 2 to 5 uniqueness, and I can guarantee the uniqueness of a solution from 2 to 5. If you ask me what's going to happen from 6 to 8, I don't know. There might be two solutions in that region. There might not be. So for example, in this case, let's just say that I can only get, let's take a look at this one. Let's take a look at this case, right here. In this case, let's just say I can only guarantee the unique solution in here. It is possible the solution might extend this way. There might be another solution coming off of this, might not intersect in here, but it may intersect there because I don't know, because we don't know what's going to happen outside. If you only know that the function satisfies, the initial value problem satisfies these two conditions only in this region, right? So if it only satisfies only in this region, I can only guarantee the uniqueness only in this region. Beyond what's going to happen, it may still be a unique solution, it may not, but I don't know, right? We cannot guarantee that. But as far as the problem that we are dealing with right here, for this particular problem, since it's continuous on the entire real line, since it's a partial derivative is continuous on the entire real line, I can guarantee for this problem the solution is unique, right? And so therefore, if you take a look at this particular point, now I can come up with a new initial value problem, right? Let's just say this is a comma b, right? This a comma b. I know this one because the function is different. The function is continuous on the entire real line. The function is continuous on the entire real line, and the partial derivative is continuous on the entire real line. I know that even for this problem, which is y prime is equal to y, and y of a is equal to b. It's a new initial value problem, right? It's going to have only one solution. But the problem is, if you take a look at this, neighborhood, I have two solutions passing through the same initial condition. That is not possible. So therefore, we can say for this particular problem, no two solutions will never intersect. That's number one. Number two, that means another thing that's going to happen. If a solution that starts below one solution, it has to remain below. It cannot go above. If a solution that starts in the middle, it's going to be stuck between these two solutions. Otherwise, what's going to happen is that if it has to go above, it's going to intersect at some point. That's not possible. If it has to go below, it's going to intersect, and that's not possible because at this point, we'll have two solutions. And that's not possible. And so therefore, we can say all the solutions are nicely packed, nicely ordered. If one solution that starts above, here, like here, it's going to stay above. For solutions that starts below, it's going to stay below. If a solution that's going to start here, by the way, the solution for this would be 0, y is minus 1. So it's going to be negative e to the x. It's going to go like that. So the solution that starts here, right, starts here is going to be between these two. It can never intersect here. It can never intersect over there, right? That's a very, very important observation that we'll be using it for the next set of things, and especially phase plane argument and so on. So this is one of the, again, geometrical implications of the Pickett's theorem. From the geometry, we can get that. And also, this also gives you a nice, a way of visualizing the solutions. One other thing that I also want to talk about in here is I also want to take a step back. So what is the differential equation anyway? right? What is a differential equation anyway? How do I find the solution to that differential equation? So let's take, even a primitive approach, even a very basic, very basic things, right? Um, all right. So let's take a look. Let's take a look. What does this mean? What is the meaning of y prime is equal to y and y of 0 is equal to 1? Let's see, how do I find the solution? Again, I'm not showing you so far. What I've shown you is what are the terminologies, and someone gives you a solution, how to verify whether something is a solution or not, and then we can also see if two solutions intersect and so on. So these are general things, but I have not given you a single method yet. I have not given you a single method, single technique yet to find the solution to a differential equation. So very basic, primitive, very basic idea would be by looking at the geometry and try to find the solution or try to solve the differential equation. So let's see how do we do that. So I'm going to graph it. So this one says y prime is equal to y, right? Y prime is equal to y is the differential equation. And I'm supposed to start at y of 0 is equal to 1. When x is 0, y is equal to 1. So I'm going to start right here. Now, how do I move, right? The solution is going to move, right? If you take a look at this here, the solutions are, take a look at this here, the solutions are moving. It's going this way, it's going this way, it's going this way, it's going this way. So now, how is it going to move? How do I figure that out? Now, this tells me that y prime is equal to y. That means the derivative. What is the derivative? Rate of change, right? Rate of change. You remember the rice overrun business, right? Rate of change at 0 is equal to 1. At this point, it is 1, right? Which means if I run 1 unit, I'm supposed to rise 1 unit, right? The rice overrun is 1 unit, right? It has to be equal. So which means if I start here, approximately, if I start here, then I would be going towards, because the derivative is, since the y is equal to 1, since that y of 0 is equal to 1, that means y is equal to 1. That means at this particular point, your y prime is equal to y and the y value is 1. So therefore, your y prime is equal to 1. Since its y prime is equal to 1, it's moving this way at this point, right? So which means it's going to go to, it's going to try to go to this point. At this particular point, right? At this particular point, what is your y? What is your y prime? Y prime is equal to y, and y in this case is what? If this is 1, if I moved 1 unit right here, I'm supposed to move 1 unit over there. I'm approximating it here, right? So it's going to be 2. So y is going to be 2. So at this point, the derivative is 2, which means I'm going even faster. So for 1 unit I move this way, I have to go 2 units now, right? So I'm going to go in this direction now, right? Now, what point is going to be? This point is going to be 4. At this particular point, the derivative is, at this particular point, the derivative is y value is 4. So which means for 1 unit I'm moving this way, I have to go 4 units up. So I'm going to go really even steeper, right? And then if I kind of combine all of them together, you see I have this kind of like exponential growth, right? There's this exponential growth, and that's what I say. I have y of x is equal to e to the x. And that's what we have right here, right? So this is called directional derivatives, right? This is called directional derivatives. So directions field, I'm sorry, but this is called directions field. So at any point for a given differential equation, we can kind of say if the solution is starting at this point, how it's going to go. Think of this way. The differential equations are like a GPS, right? It tells you if this is a car, if this is a car, let me copy paste it. If this is a differential equation, right? So if this was a car, they were starting here. If this is a car, and I don't know, my car is not good, right? If this is the car, they're starting here. This tells you to stay to follow the differential equation. You're trying to go follow the differential equation. You're trying to basically track. You're basically tracing the solution. When you're tracing the solution, this differential equation tells you, well, you have to go, 45 degrees at this particular point. Then you keep on go, you keep on track, right? You keep on track that. You keep on track that, right? Then you kind of keep on go this way, and this path is the solution to that differential equation, right? So this is kind of like a GPS, kind of tells you the differential equation is kind of a GPS, tells you how much you turn to stay in the path of a solution. And if you track the path, if you track the path, and that path is actually the solution, this path follows, the differential equation that you have right here, and that gives you that curve is what the solution to that differential equation. And these are very, very important. So even if you don't know how to solve them, by just looking at this geometry, we can kind of guesstimate the solution, how it's going to behave. So that leads to what we call directions field. So what is the direction field? So if you have a differential equation, I think I'm using the same one. I'm going to use the same one again and again, so that you can follow. If you have the differential equation y prime is equal to y, the direction field for this, the way that you would do this is the following. You would make the y-axis and then the x-axis, right? And then you're going to have points, right? You're going to have, let's just say, I'm just going to make it up, this is 0, 0, and this is, 0, 1, 0, and 2, 0, 3, 0, and this is, 1, 1, 1, 1, and this is 2, 1, and this is 3, 1. And this is 1, 2, and this is 2, 2, and this is 3, 3. So you look at the derivative, and then based on the derivative, the derivative, the tangents, you remember the tangents from your calculus and calculus 2, right? The derivatives are nothing but the slope of the tangent, right? So we try to find the error. At 1, y value here is 1, so therefore the derivative is 1. The derivative is same as the slope of the tangent, so which is 1. That means it's 45 degrees. It's going to go that way. So that's the direction. If a solution is going through that point, it must go in that direction. If a solution is passing through this point, it must go in the direction. It cannot go down. It cannot go straight. If a solution is, for example, here the y prime is 0, right? The y prime is equal to y is 0, so it's going to go in this direction. At this point, y is 0, it's going to go in this direction. At this point, y is 0, it's going to go in this direction. At this point, the y is 0, it's going to go this direction. At this point, y is 1, it's going to go that direction. At this point, y is 1, it's going to go that direction. At this point, y is 2, so it's going to go a little bit steeper. Y is 2, it's going to go a little steeper. Y is 2, it's going to go a little steeper. Why is that? Because this y prime is equal to y. If it's y squared, then it's going to behave differently. If it's a square root of y, it's going to behave differently. If it's a cosine y, it's going to behave differently, right? And then, let me also show you a few other things on the bottom. Here is x is 0, x is 1, y is negative 1, and here is 1, 2 and negative 1, and here is 3 and negative 1. Here it's a negative 1, so the slope is negative slope. It's going to decrease. It's going to go this way. Here it's going to go this way, and here it's going this way. And this is called what we call the direction field, right? This is what we call the direction field. And using this direction field, we can kind of guesstimate how the solutions are going to behave, what are the dynamics of the solutions, and so on. So for example, here you see, here's a direction field for this differential equation. That is dy over dx is equal to 0.2xy. And you see that that's the direction field. You see that how the solutions behave. So it seems like the solution is kind of going along this way, going along this way, going along this way, going along this way. Excuse me. And here are the solution curves, and for that particular differential equation. So if a solution that starts here, that's an initial value problem, right? And the solution is going to be this one, and you're going to have only one in this particular case. If the solution starts here, The solution is going to go like that. So that's the solution to that initial value problem. That's a solution to this initial value problem, same solution to the initial value problem, same solution to the initial value problem, same solution to the initial value problem. And again, by the Pickett's theorem, we can also say this is not going to intersect, right? This is not going to intersect. And this is called the direction field. And using the direction field, we can kind of look at the solution in a holistic way. And by the way, these are all called qualitative behavior of the solution. We'll talk about more in a moment, but let me just quickly tell you, what do I mean by qualitative? I haven't solved the problem, right? By just looking at this. Here, I solved it. Here, this is a qualitative, this is the quantitative. I can tell you when I say that, y of x is equal to e to the x, I know when x is equal to 5, what is the solution would be, right? In this case, it's 0. When x is equal to 3, it's a 0. When x is equal to 4, it's a 0. For this particular problem, when x is equal to 1, it's e. When x is equal to 2, it's e squared. When x is equal to 3, it's e to e cubed, and so on. So I know exactly the solution. By doing this way, we can kind of see how the solution behaves. We can, what we call qualitative, not a quantitative, a qualitative behavior. We can kind of see in this particular one, as x becomes larger and larger, y also becomes larger. As x becomes smaller and smaller, y goes to 0. So for example, for this particular problem, again, I did not solve it. I can say this solution, this initial value problem, that y prime is equal to y without solving, right? Y of 0 is equal to 0. The solution is going to have the following property. If this one has a solution, y of x, again, I don't know what the solution is, right? I don't know what the solution is, but I know for a fact when x going to 0, if limit of x going to infinity, when x goes to infinity, right, the y of x, the y value must also go to infinity. So it has to go up. It has to go up. Similarly, I can say when x going to negative infinity, y of x is going to go to where? When x goes to negative infinity this way, the y of x, right? The y of x is trying to go what? Trying to go slowly, getting closer to the x-axis. That means it's going to go to 0 right here. Again, I did not solve. By just doing this analysis, we can kind of see the qualitative behavior of the solution. So for example, for this particular problem, we know that when x goes to infinity, the solution goes to infinity. When x goes to negative infinity, the solution still goes to negative infinity. Again, we did not solve it. By just looking at the direction field, we can make this conclusion regarding the qualitative behavior, right? It's called qualitative behavior of the solution. All right. Now, having said this, let's try to use this and try to figure out this next set of things. There's something called autonomous differential equation. And by the way, this works with, you should, basically the homework A or the worksheet A is basically covering this autonomous differential equation, and then, this direction field and so on. So what is this autonomous differential equation? So autonomous differential equation is a special kind of differential equation. Basically, the derivative depends on the function itself, explicitly the function itself. What do I mean by that? In generally, the differential equation is y prime is equal to f of x comma y. What do I mean by that? An example would be, y prime is equal to xy, right? Or you can say y prime is equal to 1 plus x times y. Or you might have y prime is equal to, xy plus x squared, right? And so on. So these are not autonomous differential equation. The autonomous differential equation is something like this. Y prime is equal to f of y. You can only have explicit functions of x. You cannot have explicit functions of, you can only have explicit functions of y. You cannot have explicit functions of x in them. So for example, you can have y prime is equal to y, the one we have been talking about for a long time. Or you can have y prime is equal to y squared minus y, or you can have y prime is equal to sine y, and so on. Any function, or you can have, it's not easy to solve. Even if you want, you can have y prime is equal to e to the y, right? Those are just functions of y alone, right? There is no explicit involvement of the x. Although Y is a function of X. Y prime is a function of X. There's a X is in there implicitly, but that should not be in there explicitly as you see them in here. These are not autonomous differential equations, right? These are not autonomous differential equations. These are differential equations, but not autonomous. These are autonomous differential equations. This is an autonomous differential equation, and these are, autonomous differential equations. So there are some good things with the autonomous differential equations. Let's take a look at some of these terminologies, namely equilibrium points and critical points, phase portrait, phase line, phase plane, and stability, and so on. So what is the equilibrium point? So when you have a differential equation, which is something like this, y prime is equal to f of y. What do? You set the f of y equal to 0. You set the f of y equal to 0, right? And the y values, not the x values, the y values are called critical points, right? The value of y, that makes the f of y 0, or that makes the derivative 0, are critical points, right? Or also known as the equilibrium points, right? So you can say critical, I shouldn't say critical points because these are functions, right? Technically y is a function, but they are constant, so we are okay. Critical points or equilibrium points. So for example, if you have the y prime is equal to, let's just say, y times 1 minus y. I have this differential equation. Again, we are talking about autonomous differential equation, not an initial value problem. So this one does not have initial value, right? Not yet. Now, here's my f of y. That's my f of y right there, right? So my f of y is y times 1 minus y. When I set this equal to 0, I'm going to have y equal to 0, comma 1, right? Those are functions, not constants. Those are functions. Those are constant functions, more precisely, right? And they are called equilibrium points. And by the way, these are also solutions. They are not just points. What do I mean by solutions? The function y is equal to 0. When I plug it in to this y prime is equal to y times the 1 minus y, you know that since it's a constant, the derivative is 0, the left-hand side. And if I plug it in, since y is 0, 0 times anything is 0 is 0. So it satisfies the differential equation. So this is also a solution. Similarly, if I take a look at the y of x is equal to 1, we write it this way, right? If you remember your calculus 1, that this means, by the way, y of x is equal to 1 for all x as a function. That's what we mean by this. When we say y 3 lines equal to 1 means y as a function. Again, if I find the derivative is 0, right? And the left-hand side, let me change the color so you can see it better, so you don't confuse this with the other one. Let's go with this color. So the left-hand side is 0, right? Because the derivative of the constant function is 0. The right-hand side is, this is 1, but this is 1 times 1 minus 1, which is 0. So therefore, that's a solution. So these are not only anythings, they are also solutions. In other words, if you take a look at my phase, is what I'm going to call phase plane, or phase line, phase plane, that y equal to 0 function, right? That's a solution. Y equals 1, right, is a solution. The constant functions are solutions, right? So this initial value problem, now I can take any points in here and make an initial value problem, right? This would be a solution. That will be only one solution. I can also say, remember we talked about last time, since the function is a very nice function, it's a continuous function, continuous in the entire real line, we can say now, if a solution that starts in the middle, in between, has to stay in between. It might go up, it might go down. We'll see what happens there. But if it starts here, it's going to go like that. It can't go up. It has to stay in the middle, right? It has to. This have a special thing. We'll see in a moment how it is. It's going to go like that. If a solution that starts here, it has to be like that, right? If a solution that starts here, it has to be like that. It cannot intersect here. It cannot intersect there, right? So the solution that starts between 0 and 1, because they are solutions, right? The 0 is a solution. 1 is a solution. If a solution starts in the middle, it's going to get stuck between the upper solution and the lower solution. right? So that's, we'll talk about in a moment, more things on that one. So that's another observation, right? So these are called critical points. And again, you can find the critical points for many problems. I think you will see them, some of them anyway. Um, let me give you one more example, and then I will move on to the next set of things. What is another thing? Another thing that I want to tell you, let's just take a look at this one. Y prime is equal to, let's just say I have, y squared minus 1 times y squared minus 4, right? Now, this is my f of y. If I set this equal to, this is my f of y. If I set my f of y is equal to 0, if I set my f of y equal to 0, I'll let you solve it. You're going to have y is equal to plus or minus 1, and y is equal to, and plus or minus 2. That's going to give you 4 equilibrium points. As a matter of fact, 4 solutions. If you graph them, the solution space, if you graph the solution space, right, the solutions are going to be, 0 is one of one, so 0 is not one of them in here. -1, +1, and -2, and +2. These are all solutions, right? And this is not a solution though, right? This is not a solution. That's just x-axis. That is just an x-axis. That's not a solution. This is a -1. This is -2. This is +2 and +2. They're all solutions. Another observation is if a solution that starts here, it's going to stuck in here. If a solution starts here, it's going to stuck in here. If a solution starts in here, it's going to stuck in here. Solution starts here, it's going to stuck in there. Now let's take a look at the behavior of what's going to happen in between, right? Let's see what's going to happen in between. Let's take a look at this problem. Let's take a look at this problem and then see how does the solution is going to behave, right? In between. Let's take a step back. So I have this differential equation that is, y prime is equal to y times the 1 minus y. And I'm trying, this is what we call a phase plane. So we're trying to, now what we are doing is we're trying to find the qualitative, not a quantitative, a qualitative behavior, how those solutions are going to behave. The very first thing that what you do, the step one is to find critical points or equilibrium points. I'm going to put EQM. You understand what I mean by that. In this case, we know them, and that is y is equal to 0 and 1. We already solved it, right? Then I am going to make my y-axis, and I'm going to have my x-axis. Right. So here's my x-axis, and here's my y-axis. And so I'm going to then graph my solutions, equilibrium points. 0 is 1. Let's just say that is 1. And 1 is also another one. So we have 2 solutions, right? We have 2 solutions, and this is y is equal to 0, and this is y is equal to 1. Now, suppose if a solution that starts here, let's see what's going to happen. Let's see what's going to happen. At this point, looks like, x is 0 and y is 1/2, right? Now, let me plug this value in here. Let me plug this value in here, right? Let me plug this value in here. When I try to plug this value in here, I'm trying to see what's going to happen, right? How the solution is going to behave. Either the solution is going to go up, the solution is going to go down, or the solution is going to go straight. The solution will go straight if the slope is 0. Solution is going to go up if the derivative is positive. The solution is going to go down if the derivative is negative, right? That's all it is, right? If it's negative, it's going to go down. Positive, it's going to go up. If it's 0, it's going to go that way. Now let me plug in y is equal to 1/2. Remember, we're dealing with the autonomous, right? So when I plug in, what's going to happen? So let's just say, at x equal to 0 and y is equal to 1/2, what you have is the y prime, the derivative is, it's 1/2 times 1 minus 1/2, which is, again, I don't care about the, the value. All I care about is the sign. It's a 1/2 times 1/2. It's a positive. This, by which I mean, I'm saying it's a positive, a short form that I used to write as a positive, right? Positive. That means the derivative is positive. That means the solution has to go up. So it's going to go up, right? But as long as I'm here, by the way, as long as I'm here, if I'm right here, still the derivative is going to be positive because the number is greater than 1. This right here, number is greater than 1, so this is going to be positive, and this number is less than 1, so this is also going to be positive, so it's going to be positive, so it's going to go up. The number is still positive, the derivative is still positive, go up, go up, go up, go up, go up, it's going to keep on go. So the solution is going to keep on go like that. The question is, can it ever go this way? Is it possible the solution can intersect? It won't intersect. That will violate the Pickett's theorem, right? So that will never happen. So which means the solution is going to keep on go this way. On the other side, it's going to go that way. On the other side, it's going to go that way. So let me choose a different color so you can see it better. The solution that starts right here, is going to go like this. If a solution that starts right here is going to go like that. It can intersect any other solution. If a solution that starts right here is going to go like that. Similarly, let's take a look at a value right here. Let's take a look at a value right there. It looks like, 1.5, x is 0, y is 1.5. When x is 1.5, when y is 1.5, this is positive, but this is negative. So I'm looking at, y times the 1 minus y. This is positive, but this is negative at 1.5, 3 over 2, right? So now the derivative is negative. Since the derivative is negative, negative, right? And the solution has to decrease, so it's going to go down like that. Again, there is no bound, so it's going to keep on go forever. If I start a solution here, it's going to go that way. If I start a solution here, it's going to go that way. And let me take a look at something over here. What happens if you have something over here? Let's just say this point looks like, x is 0, y is negative 1/2. When I plug this into, again, the differential equation, which is, y prime is equal to y times the 1 minus y. Since it's negative, this is a negative quantity. 1 minus 1 is positive. That's a positive. So altogether it's negative. Altogether it is negative. So therefore the solution is going to decrease. So the solution is going to go down like that. If a solution that starts here, it's going to have the same behavior like that. Solution that starts here is going to same behavior like that. Now I can actually analyze. This one and say how does the solutions are going to behave, right? How are the solutions going to behave in this, in this one? Hold on. Let me just, move these things up a bit. And by the way, this is called phase plane. This is called phase plane. And this is the phase plane, more precisely of the differential equation y prime is equal to y times the 1 minus y. Now let's try to look at some of the things. Now let me give you an initial condition and see what are the things that we can decide about the qualitative behavior. If, let's take a look at this, y prime is equal to y times 1 minus y, and if y of 0 is equal to, I'm just going to say 3/4, a number between 0 and 1. The number is right here, somewhere over here, right? What happens for this initial value problem? Let's just say I have a solution. I'm going to call the solution as, y 3/4. So what do I mean by that, right? y 3/4. Now, what happens to this y 3/4? What happens when x goes to infinity? What happens to y 3/4 of x? As you would see, when x going to infinity, the solution that starts here, it's going to go, but it can never touch 1, but it'll get closer and closer to 1, so it's going to reach 1. So therefore, this is going to be 1. Similarly, if I ask you, take a break. If I ask you what happens to limit x going to infinity of this solution, the same initial value problem, sorry, negative infinity, what would happen? When x goes to negative infinity, ladies and gentlemen, you see that it's going to go to, eventually it's going to go to 0. Right? Again, we can make a qualitative assessment of the solution without actually, we did not solve it. We did not solve it. We just, use some geometry. We used some, our calculus one, function is increasing, function is decreasing, whether if the derivative is positive or the derivative is negative and so on, right? We can do that. Now let's take a look at another initial value problem. Let's just say I have this initial value problem. Let me change the color, which is y prime, the same differential equation, right? And let's just say y of 0 is equal to -1. It's somewhere over here. It's somewhere over here, correct? It's somewhere over here. And you see the solution is going to go to negative infinity when x goes to infinity. X goes to infinity. Solution is going to go to 0 when x goes to negative infinity. For this one, I'm going to call the solution, I'm going to write as a y -1. For this one, if you ask me what is the limit x going to infinity, y -1 of x, that's going to be negative infinity. And if I ask you, now you should be able to tell me what happens when x goes to negative infinity of the solution that we call y -1 of x. That's going to go to 0, right? And that's how we can analyze the qualitative behavior of the solution by just looking at the phase plane. There's something called a phase line. What is that phase line? Phase line is very simple. This is a two-dimensional phase plane is a two-dimensional version. Phase line is a one-dimensional version. What do I mean by that? So you mark the critical numbers, right? You mark the critical numbers. Here is a 0. Here is a 0. And here is your 1, right? And in this particular region, the derivative is negative, right? So I'm going to make an arrow. The solutions are going down. In this region, right? The derivative is, I'm sorry, I think I made a mistake in here. In this region, the derivative is positive, so the solutions are going up. In the orange region, the derivative is negative, so therefore it's going down. And in the below 0, let's go with some red, right? In this region, the derivative is still negative, right? So it's going to go this way. It's going to go this way. And this one-dimensional line is what we call the phase line. This is called the phase line. So that's how we would solve. That's how we would find the equilibrium points, critical points. Phase portrait is also known as the phase plane, and phase line we just talked about it. Let's take a look at the stability, and we will move on. So what is the stability? The stability is something like this. When we say stability, we're talking about a stability of an equilibrium point. So if you have an equilibrium, let's take a look at the one that we have. So if you take a look at the one that we have, here's my 0. And let me copy paste to make my life easy. Clear the things that I don't want, I don't need. All right. So if you take a look at this equilibrium, point or equilibrium solution, if you take a look at this equilibrium point or equilibrium solution, right? What you have is any solution that is starting nearby. This one is kind of like attracting. All the solutions are, whether it's up or down, it's all getting closer and closer to that value, right? And so this is called stable equilibrium point. This is called stable equilibrium point, right? This is stable. And if you take a look at this one, this guy right here, right? Any solution that starts nearby, it's kind of going away. It's not trying to get to this one. It's trying to go. It's going away, right? So this is the unstable equilibrium point. Sometimes you may have a case, that might look like this. So this might be an equilibrium point, this might be an equilibrium point. It might go this way, it might go this way, and this also might go this way. What do I mean by that? In one direction, this is an equilibrium point, that's my equilibrium solution. In one direction, it's attracting, in other directions, it's repelling, right? This way, when a solution that starts below, it's going away. When a solution that starts above, it's getting closer, right? So this has like an attraction on one side, repelling on the other side, and this is called semi-stable. This is called semi-stable, and that is the stability of an equilibrium point. And again, I think take a look at the homework A. You will have, a problem there to solve it for you. Try to solve that, and if you have any question, I'll be happy to answer. That's pretty much is about this phase plane and phase portrait of autonomous differential equations. All right, let's take a quickly, and again, we can use this, we can use the differential equation to solve various things. And I think here's one application right here. This is from your book, right? So in anything that you try to model that deals with time, that deals with growth and so on, you're trying to predict the future. So when you're trying to predict something, you're trying to see what's going to happen in the future and so on. So when you do that, the way that we predict them is based on the data that we have from the past, right? So how the things are changing from the past, using that, we are going to predict how things will change in the future, right? So it's always the rate of change is important, right? So we model, so the the derivative is nothing but the rate of change, right? Rate of change of y with respect to x. So let's just say, for example, if you want to take a look at the stock market, right? It's always a stock market, let's just, with respect to time. Let's just take a look at, a stock of an Apple, how the Apple stock changed over the past 5 years, right? For every year, for every week. It depends on what kind of what kind of investment that you're doing, right? If it's every year or every month or every week or even every day, right? If someone is people doing a hedge fund, they are looking at how the Apple stock is changing every day to predict something that's going to happen. If someone is in a pension plan, they don't care about how it's changing every day. All they care about probably how things are moving every year, right? That's what they would care about. So it's also about predicting. So which means we always deal with the rate of change. And here's a problem. Here's a nice problem about the rate of change. So here we have a container tank, and this tank, there is amount of water is going out, there's amount of water is going in, and this has some sort of a salt. And so here we are trying to model what is the amount of salt in this tank, right? Based on the rate of change of salt by coming in and going out, right? So if you take a call A of t as the amount of salt in the tank T at any time, and here three. So this is supposed to hold 300 gallons of some sort of a salt water, right? And there is 3 gallons of per minute of salt water is being pumped into this, right? And every gallon has 2 pounds, so which means 2 pounds has been added per gallon, right? Per gallon to this tank, and the whatever is inside is getting out. Whatever is inside is getting out, right? So we can model this. So how are we going to model? The change in the amount of salt is the intake plus minus outtake, right? Intake is the plus, outtake is the minus. So the input rate minus the output rate. What is the input rate? It's getting 3 gallons per minute, and every gallon has 2 pounds. So it's going to have 2 gallons 2 pounds per gallon times 3 gallon per minute. That's a 6 gallon, right? So that's 6 pounds. So you're getting 6 pounds per minute as an input rate of salt. How much is leaving? Whatever is there per amount of salt per gallon is going 3 gallon per minute. So that is going to be the amount of salt in the tank at any given time t divided by 300 times 3 gallons per minute is how much is leaving out. So it's going to be this one. So when we put them together, you're going to have a nice differential equation, something else. Again, don't worry about this. Again, we will come back and do this later time. But I want to quickly show maybe one quick example of how do we model, or basically how do we look at the model, how the differential equations are used in modeling certain things. The basic idea that I want you to get out of this example is that over the period of times, things are going to change. And when you try to model something that involves a change, the differential equation is going to play a vital role in modeling any scenario that has a change, that has change in it inherently. That's all. That is the crux, or that is the core idea of this particular example. All right, I will stop it right here, and this takes care of the chapter 1 and the introduction to that. I will see you in the chapter 2.